Okay. At which point is the approximate center of mass of the student log system? All right, we already talked about this. It's got to be at B, right? If the person were located at C, then the center of mass is in C. As the person moves to the left, the person brings the center of mass with them. So the center of mass if the person's on the left side has got to be someplace on the left side, but it certainly can't be at A because we've got all the rest of this mass over here on the right side. So the center of mass has got to be at B. And if we did the calculations using this, then it would work out. But we don't have to necessarily do the calculations. We just have to have an understanding of what's going on. All right? I'm adding a question. The new question is, as this person walks towards the end of the board towards E, where does the board end up? Zach, what did your group say back then?
We said the left.
To the left. Like this?
Yeah.
Okay, how come?
Because in order to walk forward, he has to push the log back.
In order to walk forward, he has to push the log back. Right? Hey, that's how we all walk. This person is pushing the log backwards to make them go forward. Just like I push back on the ground to make myself go forwards. All right? Zach, where's the person located?
After his walk
Yeah. When the log's located here, where's the person?
at the right side.
At the right side of the log? Like that?
Yeah.
Okay. What direction did the log go?
Backwards.
Backwards. What direction did the person go? Not technically backwards, definitely backwards. All right? Does that make sense? What direction does the person walk? The person walks to the right, which causes the log to go to the left. Andy, what'd your group say? Where's the log end up?
We said that it would end up to the left of the initial log.
So like this? Okay, where's the person?
We said it would be on position.
On position E, which is this. Okay, what's the problem with that? I just said what the problem with that is. What direction does the person walk? The person walks to the right. The person can't go backwards to the left if the person is walking to the right. John, what did your group say?
We said that it moves to the left.
Well, the question is where does it end up?
Oh, well, yeah, it ends up to the left.
So it ends up like this.
Yeah.
Is that correct?
Well, yeah, but it's not going to move like all the way past.
Okay, so where does the log end up?
Probably like E would be near like E, I guess.
E would be like near B, I guess. All right? That's the question. All right? My recollection was you sat there for the last minute and a half and didn't say anything, right? That is what we need to address in the question. Now we're getting better. Some of the log has to be over here. John says that what E would end up like at like B, I guess. So the person would end up right here. Kaylin.
Well, because the person's walking at 2 meters per second and the log's moving at 2/3 meters per second, so it wouldn't technically be all the way to the left. So it would be like kind of like what is that?
It would be kind of a, yeah. So first off, right? So what's Kaylin saying? That's the answer to B, right? It's a conservation of momentum problem here, B, right? The momentum to begin with is equal to the momentum after the person starts to walk. But the person's stationary and the log is stationary, so the initial momentum of the system is 0. Which means the final momentum has to be 0. Well, how do we get the final momentum? It's the mass of the person times the velocity of the person plus the mass of the log times the velocity of the log. Well, we know that this is, 80 kilograms and 2 meters per second, and the log weighs 240 kilograms. So the log's velocity has to be minus 0.66 meters per second. So yeah, as Kaylin says, Yeah, it's gotta be like someplace over here, right? But where's the someplace over here? Miriam or Hasmin? What do your group think?
We thought that where E is on the log would be where A was originally at the start, and that the person doesn't really move anywhere overall because there's no outside forces acting on the system, so the center of momentum is going to stay the same.
There are no outside forces. I'm gonna switch that R to is. There is no outside net force. Therefore, the center of mass of the system has to maintain its motion. Huh? Don't read.
Yeah.
Listen, here's the key idea. We are not incorporating the key idea correctly as of yet. We're getting there. We're getting there. There is no outside net force. Therefore, the center of mass of the system maintains its current motion. Well, right now, what's the current motion of the center of mass? It's what? It's at rest. And where's it located? At B. Now, if I drove a boat and hit the log, could I change the center of mass's motion? Yes. If a shark came up and grabbed the person, could it change the center of mass's motion? Yeah, but those would be outside net forces. Are there any outside net forces here? No, so what happens to the motion of the center of mass? It doesn't change. And in this particular case, since it's not moving, not changing is that it continues to not move. Where's the center of mass, Carolyn?
It's going to remain at B, and then the log is going to be at C. That's going to be the right end of the log.
Yes. How come?
Because in order for the center of mass to stay in the same location, obviously at B, we know that it's going to be about like one of the spacing units away from the person. So if you put it there and kind of draw backwards, you get to the point where it has to be right there.
If the person's at this end and the center of mass is at B, and then the person ends up at this end, where's the center of mass of the system? D. But where does D have to be located? D's got to be located where B is. Because what's the velocity of the center of mass of the log system? 0. The key idea is not that the center of mass stays put. The key idea is that the center of mass's motion stays the same if there are no outside forces. In this particular case, the motion is non-motion, or the motion is that the thing is at rest. We are always in the business of progressing. If we are always in the business of progressing, and this particular problem had the center of mass being stationary, and the key idea was that the center of mass's motion does not change if there's no net outside force. What do you think the next step is? If the center of mass is moving. Here's a problem where the center of mass is moving. Okay, look. We did a nice job here. There's actually 2 ways to look at this. Nobody mentioned the second way. So whether you got this thing written on your whiteboard and you did it in a minute and a half, there's still something new that I'm going to tell you. Okay? Now look. Yesterday, Isabella, can you turn that whiteboard around? It might still be on there. Oh, no, that's not going to work. Just turn the entire thing around. That thing's on its last legs. Get there, it would probably fall apart. All right, perfect. There we go. So if the center of mass wasn't moving, we use conservation of momentum on the left side of that board, and we use the center of mass stuff / idea on the right side of the board. Well, let's talk about the conservation of momentum way, which is how everybody did this. And then we're going to use the center of mass as a check conceptually. All right. So look, we did a really nice job. The momentum before the spring goes off must equal the momentum after the spring goes off, because there's no external forces. Here's the thing though, this initial momentum is not 0. It's 6 kilograms times 3 meters per second. 2 combined masses times the velocity of the combined mass. Well, what's that got to equal? That's got to equal the mass of card A, which is 3 kilograms, times A's velocity afterwards, plus 3 kilograms times B's velocity afterwards. What can you do over here on this side to the 3's? 3 times VA plus 3 times VB. Factor it out. 3 kilograms times VA prime plus VB prime. I get that marker. This one fits. All right. Well, what's this 3 do to that 3? What happens to these two? Yeah, numerically they cancel, right? And then I got 6 meters per second equals VA prime plus VB prime. I think everybody got to that point. What's that mean? The sum total of these two things after the collision has to sum to 6. Now look, so I think a couple of the groups did this. There's VA, there's VB. First off, VA is moving at a speed of 3 in the positive direction, and it experiences a force in the same direction. So what has to happen to its speed? It's got to go up. So the smallest amount that the new speed for VB could be would be 3.1. Let's just say, right? What would VB be then? 2.9. Now notice, this is something that nobody else did. Oh, what if this is 4? Then what's VB? 2. What if VA is 8? VB is -2. What's the difference between VT going a speed of 2 and it going a speed of -2? In the -2, it's going the other direction. Now, I didn't even pick up on this till one of the groups in fourth period talked about this. Look at it. If B is moving at a speed of plus 3 meters per second in one direction, let's say it's moving at a speed of 3 meters per second this way. If a force acts this way, does that automatically mean that the object has to go that way? No. Like, look, if I'm walking this way and Emmett tries to stop me, I'll barely notice it. I'll just keep walking in this direction. Just because he's exerting a force on me doesn't change my direction. It might slow me down a little bit. So the cart doesn't have to go in the negative direction. I think all of your examples had a positive over here and a negative over here. Now, those are possible as long as they add numerically to positive 6, but they don't have to go in the opposite directions. John, how could there possibly be these different answers?
Depending on how strong the spring is, it could exert a different force, causing different velocities.
Perfect. All right. If the spring is barely to spring it off, we're here. If it's a stronger spring, we're down here. Now, how can we use center of mass to describe this? Well, look. If these two carts, and let's pretend that they're infinitesimally small carts, so that they're both actually located at x equals 0, when they are traveling together at a speed of 3 meters per second. Okay? So the center of mass is at x equals 0, the speed's 3 meters per second. As long as there's no external forces, what happens to the motion of the center of mass? It keeps going, in this case, 3 meters per second. So, 1 second later, where would the center of mass be located? 3 meters away. 1 second later, at x equals 3, the center of mass of the system would be here. If the speeds were this, how far is this thing going to go in 1 second? 8 meters. So where is cart A going to be located? Cart A is going to be way over here at x equals 8. Where's cart B going to be located if the plunger goes off at x equals 0? X equals -2. Where's the middle of 8 and -2? 3. No, the plunger goes off at a location of x equals 0. Okay? And its speed is literally -2 meters per second. It's not the vector summation of these things. It becomes -2. So it goes -2 meters per second back in that direction. It's not the vector sum of those two things anymore. So we can describe this through conservation of momentum, and we can describe it through center of mass. And tomorrow, we take all of this stuff and start talking about how it relates to rotation. So the location of all of our forces now matters because we're talking about rotation. All right, do me a favor, erase the whiteboards for me and put them back